said it wasn't a video check.
All right, welcome to Analysis 1A, Lecture 15. Craziness is happening, tons of snow, tons of park testing, and other things. I have not seen you. I forgot pretty much all of your names. I haven't seen you in like a week, but we're back and we're going over some homework. One homework we already went over in the last video, and the other one was some homework on basically logarithmic differentiation. Let's do like 2 or 3 of these. Which ones would you like to do, class? Thoughts? 71. We can do 71. We can do
67.
67. Okay. Is that pretty much good enough? I feel like that's kind of good. Yeah. Okay, so what was 67? 67 is one of these problems which does not require you to use implicit differentiation, but it's certainly a good idea. So you have x squared over root 3x minus 2 over x minus 1 squared. The goal is to differentiate this. So what we're going to do is we're going to take the natural log of both sides. Can I kind of like skip steps and just like and just like show off? Yeah, so we take the logarithm of this whole thing, and then I use a bunch of log rules all at once. What I get is 2 ln x plus 1/2 ln 3x minus 2 minus 2 ln x minus 1. And now we have barfed on our function, split it up into tiny, nice, easily digestible pieces, and now we can differentiate both sides with respect to x. So when I differentiate ln y, the derivative of ln y is 1 over y dy dx. And here we have, I guess that's like 2 over x plus 1/2 times the derivative of ln of 3x minus 2 is 1 over 3x minus 2 back inside 3. And this is minus 2 times the derivative of ln of x minus 1 is 1 over x minus 1 back inside 1. And so we get that dy dx is y, which is x squared root 3x minus 2 over x minus 1 squared, times like all this stuff. So 2 over x plus 1 over 2 3x minus 2, or no, I guess that's a 3 up there, minus 2 over x minus 1. Bam. Who had a question about that? I feel like that was a pretty straightforward problem. Whatever. Cool? Judy, cool? All right. We do 71. 71 is x to the 2 over x. So, okay, this is pretty fancy. So we should probably be careful about this. I'm going to rewrite this as y equals x to the, and that exponent, 2 over x, is really like 2x to the negative 1. I feel like that makes it a little bit more clear what's going on. All right, so this is not an exponential function, nor is it a power function, and so if I want to differentiate this, I have to use like advanced techniques. And basically we have to rescue the princess. We have to bring the exponent down somehow. So we take the log of both sides. This is a problem in which logarithmic differentiation is obligatory. And now we use the log rule to bring that down. So I get ln y equals 2 to the 2 times x to the negative 1 times ln x. And now I can differentiate this side implicitly. Derivative of ln y is 1 over y dy dx. And now I just use the product rule. So derivative of the first, negative 2x to the negative 2 times the second, plus the first times the derivative of the second, and the derivative of ln x is 1 over x. So actually we can simplify this right-hand side a little bit, because this is negative 2x to the negative 2 ln x, but then this is also going to be a plus 2x to the negative 2, right? Yeah. So what we actually have is 1 over y dy dx, and this becomes like, I don't know, this is like 2x to the negative 2 times 1 minus ln x. It's looking good. So my final answer is that the derivative dy dx is y, in other words, that thing, x to the 2 over x, times all this stuff. And all this stuff is, I guess it's like 2, 1 minus ln x, all over x squared. Did they leave it like that in the book, or did they do more simplification? Wait, that looks good to me. You good?
Yeah.
Okay. Can I have this homework also? Unless you have a question, can we hand it in right here?
I think in the book, they x squared x to the negative 2 and then combined it with the...
Yeah, so it's like x to the 2 over x minus 2, like that?
Yeah.
Well, you want some?
Like that?
Sure.
Is that what it is? Yeah. Yeah, it seems like the kind of crap textbook we do. Wait, no, piles are all... Oh, this is okay. Yeah, if you did them on the same sheet of paper, then I guess put them both here and something, put it here. Yeah. Cool, all the homework on the back. Can you write like a more detailed, like 2 homeworks together? That's kind of vague. Like, can you write this homework and also the page 172 homework is included on the back or something like that. All right. So the other thing, let's see. We did nap time. We went outside.
Will, open the window.
Okay. So the other thing that we did last week, you did it via video, is we learned how to differentiate the inverse trig function. You guys all printed that packet? Can you get that out? Oh, how'd that happen?
He gave us that had amazing foresight.
So I just passed it out?
Yeah.
No wonder why I was missing like 20.
Yeah, that makes sense.
That explains that. And all mysteries will eventually be solved, except for my missing clipboard, which is a major problem that I'm worrying about. All right. So on the video we did the derivatives of arctan and arcsine, and all that was left was arcsecant, which is the hard one. So let's talk about that. So but the derivative of arccosine, it turns out, is pretty much just the opposite of the derivative of arcsine. Nod vigorously if you agree with that conclusion. Yeah. And then the derivative of arccotan is the opposite of the derivative of arctan. Which is fascinating. Which, by the way, can someone say something smart about why that's not such a surprise? For example, that the derivative of arccotan is just the opposite of the derivative of arctan. Is that like a shocking fact, or is that like obvious to you?
Arctan like to the negative first. Yeah.
No. Classic Griffin. No, not true. Is arccotan just 1 over arctan? Definitely not. No way. No way. Yoni.
Arccotan is like, it's like flipped vertically and then moved a bit.
Yeah, I mean, right? What is arccotan look like? Arccotan has like a thing at pi, as you reviewed. It's just like a sideways cotan. So I guess it's like this, right? Did I do that right? I feel like I did. Yeah. That's arccotan. So I'm not quite sure how it's changing, but it's like going to be 0 minus, and then it's going to be -1, and then it's going to be 0 minus again, more or less. Well, what does arctan look like? It's the same shape, basically. I guess this is the key point, is that it's more or less just the same shape, just exactly like he said. Since this is arctan and this is arccotan, what's the kind of relationship between these graphs? Well, arccotan is just arctan flipped over the y-axis and then moved up by pi over 2. And so if you're talking about the derivative of this function, then you're talking about how this function changes, and the way this function is changing is exactly the opposite of the way this function is changing, right? This one's like a tiny negative, and it's getting smaller, becoming -1, and then you're going back to a tiny negative. This one's a tiny positive, and then it's going up to 1, and then it's going to 2. So it's like the same thing. It's like the same shape. All right. Goal for this page 5, let's figure out the derivative of arc secant. You already did it, so thus I'm going to go really fast. So it's like a 4-part thing. First of all, we graph y equals secant x, and you're just expected to know this. So, you know, here's negative pi over 2, here's pi over 2, pi, 3 pi over 2, etc. When someone tells me to graph secant, what? No. When someone tells me to graph secant, I pretty much graph this. But unfortunately, secant is not 1-to-1, so we need to pick an interval when we restrict the domain, and the interval we pick is the interval from 0 to pi. So that's a thing. Thus, when I go, this is your last chance in your life to finally learn the inverse trig functions. What does arc secant look like? Well, as there's a vertical asymptote here at pi over 2, there will be a horizontal asymptote on the inverse function. And then normally I'm at 0, 1, so that would be like 1, 0. And normally as I'm a little bit less than pi over 2, I go to infinity. So thus, as I go to infinity, I must go to a little bit less than pi over 2. And over here, if I'm a little bit more than pi over 2, I'm at negative infinity. So as I go to negative infinity, I must go to a little bit more than pi over 2. And then there's pi negative 1. So negative 1 pi. Yeah. So you guys got that for the graph of arc secant? Okay, good. Then your task was to conjecture what you think the derivative of arc secant should look like. So what should it be? Well, I guess, first of all, it's going to be defined only from negative infinity to negative 1 and from 1 to infinity. And to me, it looks like it's going to be a tiny positive, and then it's going to be like infinity pretty much, right? So tiny, so I guess some kind of crazy function that looks like this. And then over here, it's going to be more or less infinity, and then it's going to be eventually a tiny positive. So I got something like that. Do you agree? All right. Thank you. Thank you. Yeah. Okay, so now we actually do the math. So here comes the math. I have y equals arc. You're like moving the camera and stuff, right?
It's been on the board the whole time.
Awesome. Y equals arc secant. So we do this by saying, okay, well, secant y is x. And now we differentiate both sides with respect to x. So we're going to take the derivative with respect to x of secant y, and the derivative with respect to x of x is what you guys all did. Okay, you're all looking at me like you're bored, so I'll go faster. Derivative of secant y is secant y tan y back inside dy dx. And this is just 1. All right, so what I get is that dy dx is, I guess it's like cosine y, cotan y, or something like that. Is this what you guys got?
Yeah.
Yeah. Okay, so calculus over. Now it's just a pre-calculus problem. So the pre-calculus problem is to figure out what cosine y, cotan y is when y is arc secant. So for this, we need to make a picture of arc secant. And this is where it gets pretty confusing, right? This is the, you might recall from pre-calc C, that this was like the hard one. So when you make a picture of arc secant, it's weird. So we know that arc secant is going to always be in the first quadrant or second quadrant. If x is positive, it'll be in the first quadrant. If x is negative, it'll be in the second quadrant. So when x is positive, I'm going to draw a first quadrant angle. And when x is negative, I'm going to draw a second quadrant angle. And I have to label the sides of the triangle in such a way that the secant of this angle is x. So secant is the ratio between the hypotenuse and adjacent. So it seems like that one should work just like fine, right? And then this becomes root x squared minus 1. Make some noise if you're angry or even just excited. Do something. All right, good. Now moving over here, now x is negative. So I can't just do that same trick again, because now I want it to be the case that the ratio between the hypotenuse and the adjacent is x. But like this doesn't work, because for one thing I go left, and for another thing I can't have a negative hypotenuse. Do you remember how we solved this problem? Like advanced. Yeah. if we just make both of those negative, now everything just like works out, right? And this becomes root x squared minus 1. Now x is negative, so negative x is positive, and the hypotenuse is now a positive number. Yet this is still a picture of arcsecant because the ratio of the r to the horizontal component is still x. All right, so and now we just do it. I guess like what's cosine y in this case? Cosine y would just be 1 over x. And what's cotan y? Cotan y would be that over that. So we get 1 over root x squared minus 1. And since x is positive, that's a positive quantity, that's a positive quantity, we would expect both of those to be positive in the first quadrant. Okay, so it turns out that in this case, cosine y, cotan y is just 1 over x root x squared minus 1. But something tricky happens over here in the negative case. Now what is cosine y? The cosine of that angle is now, oh, well, it's still 1 over x. And is that 1 over x a positive or negative quantity? Let's try again. Oh man. It's like a Christmas break thing all over again. When there's been no school for a week, you guys just come back like dumb. No offense. All right. Yeah, is this positive or negative quantity?
Positive.
It's definitely negative because x is negative. We're in the x is negative case. X is a negative number, so 1 over x is also negative. Do you expect the cosine of a second quadrangle to be negative?
Yes.
Yeah, so it's looking probably correct. All right, next. What is the cotan of y? Cotan y is the ratio between like that and that, right? So that's negative 1 over root x squared minus 1. Is that a positive or negative quantity?
Negative.
Negative, because the denominator is guaranteed to be positive, so that's negative. Do you expect the cotan of a second quadrangle to be negative?
Yeah.
Cotan of a second quadrangle?
Yeah.
Yes, we do expect it to be negative. Good, good. Don't try to talk away on that one. All right. So it's looking like these are right. Unfortunately, when I go to put it all together, it turns out that cosine y, cotan y is negative 1 over x root x squared minus 1. Yikes. So apparently I have a different formula depending on whether x is positive or negative. So I could just say that this is like, it depends, or you can like use an absolute value to like take care of it, right? So this is like a how the leopard got its spots type story. Suddenly an absolute value just like appears in this formula. And the reason is because of this careful case analysis. We see that when x is positive, we get this formula. When x is negative, we get this formula. So basically to show off, we write the formula like this. And by the definition of absolute value, it is positive when x is positive and negative when x is negative. Follow? That's why there's a mysterious absolute value sign in the derivative of arcsecant. You are now one of the 0.00001% of people who understand why that is so. Good job. All right, now it's time. Will you cool? All right, now it's time to see if our guess is correct. Suppose somebody just out of the blue came. What's up?
I thought you were going to say quiz.
Oh yeah, it's almost time for a quiz. Suppose somebody out of the blue just came up to you and said, "Yo, graph 1 over absolute value x root x squared minus 1." I should have made you graph this back in like, pre-calc C, just for some of that back mapping thing that they always talk about. All right, talk to me about that function. By the way, you can kind of cheat, assuming you're confident about your guess, but pretend like you're not cheating. Say something about that function. Undefined between -1 and 1, she whispers. Yeah, that's certainly true, right? The domain of this function is going to be everything from -infinity to -1 and from 1 to infinity. I agree. Tell me something else about this function. Asymptotes at -1 and 1. Asymptotes at -1 and 1. Yep, that's true. More things. Yeah, if x is like a huge number, if x is like 1,000,000, then it's going to be 1 over, it's going to be basically tiny. Also, always positive, right? Because positive, positive. So when you put all that together, some weird noise just happened. When you put all that together, that there are going to be asymptotes at -1 and 1, says Griffin, because if you plug in numbers that are near -1 or 1, that's going to make the denominator tiny, which is going to make the thing huge. Also that it's always positive, also that it's going to infinity. You pretty much just get this shape, so things are all confirmed. Alright, so I now pronounce you experts on the inverse trig functions. Good. That didn't take too long. I mean, how you feeling? Good. Alright, did I pass out this worksheet that was like 1 page long that said like,
Yeah.
oh I did?
Yeah.
Did I sign problems from it?
No. You just gave it to us.
Interesting. Okay, so we're gonna have some classwork time now. Oh, you did it?
Yeah.
Oh, cool. So we're gonna work now, just like, we're just gonna work in groups and play some jazz and just do these problems. So, should we keep it